Okay, so it's 4:15 and time to get started. And before we get started, there is a few practical matters that I would like to inform you. So first thing that I would like you to be aware of is a message from Suraj. So Suraj mentioned that it's highly recommended you to participate the guided tutorials that will be on Wednesday and on Thursday. And why it would make sense to you to participate there, that's simply because right now you have the simulation assignment, and it really makes sense to start putting some effort to the simulation assignment. Remember that we can be very flexible, we can be even nice people, we can, but only if we see an effort from your end. So please make sure that you do your best and not to make yourself rush stuff at the very late of or very close to submission day. So please make sure that if you're facing difficulties, you get the help from Suraj this time, meaning as early as possible. And you usually get some difficulties. There's always some complications related to, if nothing else, then the modeling of hydraulics. So please use the help that you can get from Suraj. Then another note is that now the second midterm exam is designed to be in, let me think, not next week, but week after that. So we have one more lecture to go, and we can set the second midterm exam to be on right after that. And it will be the same kind of the policy, same kind of the practice than in the case of the first midterm exam. So meaning that you will have a 1 week time to do your exam, and you will have 2 attempts. Now, this Student Affairs Office and LUT administration highly recommended us to do oral exams as well to ensure that there is no wrongdoing, there is no cheating from your end. This is something that we are considering, and it's not sure how is that we can possibly organize it. But be prepared to that too. So it was not mentioned, but it's something like, in other courses, not you, of course, but other students that are got to do some kind of cheating in these online exams, and university administration is very worried about that. So we'll see. We'll see. I will keep you informed, and I will give you information on Monday, next week Monday. And next week Monday is our last lecture. And the topic is boring. It's going to be real-time simulation and games and summary for the midterm exam. So I recommend you not to come. Yes, sir. Um, in certain extent, yes. So what are the subject matters that I'm expecting you to master? I will explain all those in Monday. Well, on Monday, next week Monday, exactly the way that I did that in the first midterm exam. So each of the topics will be rated by stars. Higher the stars, the more important is a topic, and that's your way to see how is that you can focusing on stuff and what things you should learn and what are the things you maybe can skip. Okay, so that's those are the announcements. And let me see what are the online participants saying. Okay, so one guy is very happy that there's more exam. You're welcome. We're happy to help you. So no worries. And again, one thing that is good to keep in mind that this second midterm exam is easier than the first one, much easier, because we're speaking about the concept and theories that are kind of somehow down to earth. And in the first midterm exam, the concept we discussed were not so clear, like this virtual displacement and so on and so forth. This time it's going to be easier and is more down to earth. And so in that sense, that's a good news for you. Keep in mind that you still need to read it. So don't develop up-nose attitude and think that I don't need to read anymore because, I'm down to earth and I'm down to earth guy, so I can learn it without no effort. No, you cannot. You cannot. You still need to work to make sure that you pass the course. Okay, so that's about the practical things. I Any questions, by the way? The one thing that there's a comment that I have never seen that such a great comment in this chat, and the comment is saying EP is a Monday again. So I think we need to change, this thanks God is a Friday. Instead of saying Friday, we need to say thanks God is a Monday. Right. That sounds good. Okay. Any comments? Any questions? I think it is pretty clear. Okay. So with that, we're gonna summarize what is that we discussed a week ago. And a week ago, we learned that there's two different types of flows. And the one that is dominating and most important for us is a turbulent flow. And in the case of turbulent flow, the particles are whirling. So they're not traveling in order through the orifices, but instead they introduce a certain level of chaotic behavior. And a behavior where they are rolling, traveling not back and forth, but they circulating in a way that happens in a whirling. And modeling wise, the important observation regarding turbulent flow is the fact that the pressure difference and the flow rate are quadratically related. This is extremely important. How they're quadratically related, there's going to be certain parameters that are defining relation between the pressure difference and the flow rate. But pressure difference will be under the square root, meaning that that's a quadratic relation. That's something that is important to keep in mind. And as soon as you see the characteristic curve, and as soon as you see that it behaves in a quadratic manner, you know that now we're speaking about turbulent flow. Then flow type that is not that common, but takes place every now and then is a laminar flow. And in laminar flow, particles are traveling with a good order, so they are not whirling. And the laminar flow typically takes place when the pressure difference is small. Okay, what is small then? Well, that's roughly speaking, if the pressure difference is less than 2 bars, it's most of the cases safe to assume that the flow type will be turbulent flow. And now I need to check. There is a somebody's asking if there's going to be a recording from the guided tutorials. No, there are pre-recorded matters related to guided tutorials, but guided tutorials themselves are not recorded. So that's the way it goes. Okay, that's flow types. And then we learn the modeling technique that is called semi-empirical modeling approach. And one of the founding fathers of the semi-empirical modeling approach is Professor Dr. Heikki Handrus, well-known professor in LUT University. And the concept behind is very simple. You will get started from analytical expression of each one of the components. And what you then do is that you're using mathematical manipulation to express parameters not known in a way that they can obtain from manufacturer's catalog. So it's very simple. Example is a throttle valve. Analytical equation is the one that is shown here. So to be able to express the flow rate through the throttle, you need to know the discharge coefficient, which is a little bit of pain to do so. But there are pre-calculated tables that tells what that could be. But you also need to know the diameter of the throttle, And simple, clear parameter, but sometimes very painful to get. And how you can solve this problem is that you take these parameters in total and you express it as it is shown here. And this is something that is called, the CV is called semi-empirical parameter, and you can get that directly from manufacturer's catalog. Because manufacturers are offering something that is called characteristic curves, telling the characteristics of each one of the components they're selling. That's the idea. So it's a combination of analytical expressions and combination of measurements. But you do not conduct the measurements, but manufacturers will, or they did already. And that's the kind of the magic here, semi-empirical. That's where the semi is coming from. Okay, that's what we learned a week ago, and we learned about how is a direction valve, magnetically operated direction valve, and good example, how is that the model or the valve component can be modeled. So there are two steps to take. First step is to model the spool position. Now, if there is a spool that is operated by a magnet, you can make an assumption that the spool will follow the control signal, the one that is coming from the joystick or software or whatever is the way that you're controlling your system, with a certain delay. And with the certain delay, or take this delay into account, you can use this first order delay equation, very simple equation, where the input signal will be here, and this will be the time constant, telling you how fast the spool can move from one location to another. So we're cutting the corners here big time, because we are not making the equation of motion for the spool. Because to do that, we're supposed to know, or we need to know the spool mass, all the forces imposed, including the flow forces, so on and so forth. So it becomes to be very complicated. So we don't do that. But we make a simple assumption that the spool will follow the control signal with a certain delay, which often is the case when we're looking at the magnetically, or the spools that are operated by a magnet. Okay, what then? Then the next step, once we know the spool position, the next step is to model the flow through the valve. Again, we're going to follow this procedure or this concept of semi-empirical modeling approach. So we're going to use these semi-empirical parameters that are telling the size of the valve. That's going to be CV parameter, and that you can get from manufacturer's catalog directly. Then there is a spool position, which is a U here, coming from this equation once it is solved. And then the final component is a pressure difference. Pressure difference under the screw root, but because we don't want to deal with the nasty math, so we're going to use apps inside of the screw root. But because the flow can have a two direction, then we have this sign component. This can have -1 or 1, but nothing else. It's just telling you what direction to go, nothing else. Okay, and this is a scenario when the spool is moving in a positive direction. When it is middle position, it's assumed that everything is closed, which in real life will not be the case, because if the spool have a land like shown here, there will be a certain amount of leakage, and the leakage you will be seeing the leakage when you put this in a middle position, and then this is what happens when the spool is moving the negative direction, so that direction. Okay, then we learn about digital hydraulics. Digital hydraulics is a way to control the flow and pressures by using a large number of on-off valves. And the on-off valves are puppet valves, so they can only have two positions, fully closed or fully open. So it's not like a spool that can take any place you want inside of the spool house. But now it's just on or off. And when you have a number of these on-off valves, you can get the same kind of features and even better that you can get from conventional valves. Why? Well, it's mentioned that there is no leakage. Well, that I can admit, there is no leakage, as it is a case of conventional spool valves. They said that it can be more energy efficient. That needs to be some kind of clever control in a pump to make that happen. But yes, it's possible to achieve it. And what else they mentioned? I think that one drawback is that it's quite a bit of thinking, because the way you're controlling these number of on-off valves, you need to make clever control scheme to do so. Okay, so then that's it. That's about the summary. We're gonna cut the corners here a little bit. So we're gonna forget about the pressure relief valve. I'm gonna read it as a reading assignment. This is gonna be available in a lecture note. And this is one of these bit more advanced components, but let me just summarize let me just give a highlights to you, and then we will move on. And we're gonna go to next topic, which will be a cylinder, and the final component will be a pump. Okay, you're still alive, right? Okay, very good. So why is that you don't want to interact with me today? Because I look scary? Because of my new haircut? Okay, so let me tell you what happened. So on Saturday, I went to local barber shop, and we don't share the common language. And I tried to explain that take it just a little bit off, and he said, "Yeah, sure." And I came out like this. But he's a good friend of mine. We just don't have a common language. But other than that, it's good. Okay. And what about my dress today? Why is that I'm looking different than usually? Would you like to learn that too? So earlier today there was a former, well, he got his degree from this university already, I don't know, 35 years ago, and now he's a big shot officer in the industry. So he was making a visit, and I tried to please him as much as possible. So that's why I even put some effort to in my hair and the way I look. Okay, so that's about it. Okay, here's a pressure relief valve, and we discussed already how this operates. So this is typically used in a scenario where there is a pump like this. Pump is connected to tank, and the pump is producing the energy flow rate to the system. And when there is a flow rate and when there is no need to use energy, there is a valve, which is, if this is closed, what's going to happen is this pump keep on producing the flow rate to system. And because it keep on doing it, the pressure started to increase. So it will increase because of this equation. Remember this equation, which is effective bulk modulus divided by volume, flow rate in minus flow rate out. And then, there is no need to use this third component. Now, this is keep on increasing all the time, whereas this is zero. So it's meaning that P dot will go up all the time. So if derivatives goes up, the pressure goes up as well. So that's what's going to happen. So it goes up and up and up, and soon you need to do something for that. So what you can do then is that you can connect here a pressure relief valve. A pressure relief valve will be something that there is maybe I'm going to put it like this. There is a pilot drilling here, and the pilot drilling is the one that is shown here, connected like this. And if there is a pressure large enough, which is checked by this pilot drilling here, then this arrow will go here, and the flow will go back to the tank. That's how it operates. Okay, that's a pressure relief valve. Good component where there is two steps that need to be taken. You need to model the spool position, and you need to model the flow rate through this component. Analytical expression for the spool position will be like this. And to be able to compute it using this equation, you need to know quite a bit of material. Okay, so there is a question which is related to digital hydraulics. Okay, so I want to answer that. So there is a question if digital hydraulics is different than using sufficient proportional valve and control by flow and the pump. It's alternative for that. So you can use this conventional way where you have a proportional valve, control that, or you can use a lot of these on-off valves. So there are like two alternatives. Both have certain advantages and disadvantages, like we discussed a week ago. So hopefully that's enough information. I need to read this one more time because the problem in this screen is that it's very small font. And I am experienced professor already, meaning that I don't see the small font so well. So I hope that means something else too. Oh yeah, so now I got this question. So would it be possible to use proportional valves that are fully open, fully closed? Yeah, maybe. But the idea of this digital hydraulics is that you're using these affordable puppet valves that they don't cost so much, but because you need so many of them. So, and that will be the way that you can replace this one expensive proportional valve. So that hopefully clears that situation to you. But I was here, so I was explaining the equation of motion. So the parameters needed here, you need to know the mass, spring, and many different forces. And then finally, once you know that, this is how the flow through pressure relief valve goes. Now there's a lot of parameters. Big headache. So what is an idea in a semi-empirical modeling approach is that instead of using that complicated equation of motion, you're using first order differential equation as shown here to define the spool position. So it's a k dot that you're computing. And that tells you eventually how much is the flow rate through the valve. So that's a simple procedure. How is it you can model pressure relief valve? Details will not be shared, so you can take a look at this by using the lecture notes. And I'm going to move on to the next topic, and that's a cylinder. Very simple component. It's converting hydraulic pressure to mechanical force. And to do that, this is a two-way cylinder, meaning that it can be pressurized here in the piston side and here in the piston rod side. And how it works in a way that pressure that is applying here in the piston side will be multiplied by corresponding cross-section area. And that is minus the pressure that is fighting against it. Because look at this pressure, try to press cylinder to left-hand direction. So there is going to be a pressure P2 multiplied by corresponding cross-section area. That's going to be your force produced by cylinder. But there's one more component in this equation, and that's going to be a friction force. And the friction force is something that is taking a place because of the sealings that are used to make sure that there's no flow that is going through this piston here, and there is no flow that takes or comes off from the cylinder. So there is a sealing between the rod and the house of the cylinder, and there is a sealing between the piston and the house of the cylinder. So those are the two sealings. Because of the sealings, there will be a certain amount of friction forces. And the friction force, how that typically behaves, it behaves according to something that is called stick-slip friction behavior. Stick-slip friction behavior is something that you can see quite a bit in real life, even though that it sounds a little bit exotic. And how is it we can model that, and how is it we can take this third component into account, that I will spend a little while to explain it to you. Now, this friction force, it's safe to assume that there is a certain percentage of the net force. Net force is the one that is here in the middle, so that's again this theoretical force hydraulic cylinder is capable to produce. Okay, so if that theoretical force is high, then it's safe to assume that the friction force too is respective to that. So that too will be fairly high. Whereas if the theoretical force is small, the friction force is somewhat small. This is close to the normal force, which I'm sure you are familiar with from the friction behavior. So if I have friction, this coffee cup, I don't know if it is visible for online participant, but if I'm moving the coffee cup here, friction will be proportional to the force that I'm using to press the cup towards the table. If I'm really use a lot of power, like I'm, yes, capable to do so, it's going to be a big force, big friction force. Whereas if I'm just moving it this direction, it will be small friction force because the gravity will be only compressing the coffee cup against the table. So it's related to that. And then how well it is related is defined by this efficiency coefficient. And the efficiency coefficient is taking its numerical values between 0.9 between the 0.95. So it meaning that friction is ranging from 5% to 10%. So it's not super important, but 10% becomes to be significant. And then there is one more component, which is this curve that is coming from the measurements. And how are the measurements then? Well, here is an example about how are the measurements. And this is a little bit of small font, but let me read it to you. So what I have here in x-axis is a velocity. So I have here velocity of the cylinder. And this one here is a friction force, meaning this particular component. Uses something unusual here, because usually friction is either linear or quadratic proportional to velocity. That's typical scenario. I'm sure you have seen these pictures a lot where there's a friction force like this and velocity, and it behaves like this. Right. 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 Yes. So you have seen it. How the friction is a proportional to velocity, linearly proportional to velocity. Yes. Typical way that the friction is modeled. But you see, when you look at the measurements, there is something funny going on here because, obviously, friction, first of all, is not going here, but instead it's getting started here, meaning that the static friction is somewhat high. And something even more weird happens when you started to slide. The friction then drops. So friction comes down here, and then it started to behave roughly according to this scenario. So it started to increase roughly linearly with respect to velocity. But this behavior, when the static friction is high and then the friction comes down, that's called stick-slip friction. Stick-slip friction, which you can see quite a bit in real life. It's sometimes modeled or explained by using kind of brush and the ground. Something that there is like a behavior said that there is a kind of deformable beam here. Deformable beam is connected to mass here, and you're moving that this direction. So what will happen is that, this, because of the deformation of this brush, the motion becomes to be not smooth, but jumping. So it's touch, sliding, touch, sliding. Now this is the kind of the behavior that you can see quite a bit. And let me try to do the demonstration for you. So let me see what could be a good example. So let me try this. Not this. Not this. This is it. So you hear this? Oh, I'm sorry. Did I broke something? Oh, it's safe. Okay, so it's serious, but not that serious. Okay, but you hear when I'm moving this table, you see this. Okay, that's stick slip. Sliding, sticking, sliding, sticking, sliding, sticking. And that's the noise you can see sometimes when there's a friction between the component and the ground. And that's exactly what you can see in a hydraulic cylinder too. Theoretically, it looks like that the static friction is higher than the sliding friction. Or there is a point of the sliding friction that is significantly smaller than the static friction. And now this motion, and this not motion, noise you heard, because you heard this thing, this noise, that's because of we're moving between these two regions. So we get stick, sliding, called stick slip friction. Very common. Very, very common. Very common in the mechanics. But you knew this already. You knew it. All clear. Okay, why didn't you mention that you know this, or did you figure this out already a while ago? Okay, anyway, so let's move on. So pump will be the last component. And then there's going to be an example, and then we're done. Okay, the pump is a component that we are assuming to produce flow rate. You know, the flow and the pressure is like chicken egg. You know, one will happen first. And we make an assumption that pump will produce flow rate. Pressure, in turn, will take a place if you're resisting the flow rate. But if you don't resist the flow rate, there will be no pressure. Okay? That's how it is. And again, remember this equation? This equation, P dots, effective bulk modulus divided by volume size flow rate in, flow rate out. And again, if in and out are having not the same values, if you resisting outgoing more than incoming, pressure started to increase. And that's the mechanism that is assumed to behave. So what we're going to do here when we're speaking about the pump is that we're going to model the flow rate. That's it. Nothing else. So it's the source of the flow rate. And resisting it, that's going to give you the pressure. That's the mechanism behind. Now, again, we're going to use the semi-empirical approach like always. And that's to figure out the parameters that otherwise will be difficult to get. Nothing else. Now, there are many different kinds of the pumps. But pumps can be categorized to two different big categories. Fixed volume pumps, variable volume pumps. The difference is that fixed volume pumps keep on producing the flow rate no matter what. So they have no understanding whether or not the flow rate is needed. It just keep on producing it, and it's every now and then used because they have been considered to be the most reliable type of the pumps. So in certain industrial application where there's no significant need to control, the fixed volume pump will be the good choice. But more and more, the variable volume is the one that is being used. And I'm going to take a look at the comments from the chat window pretty soon. These are the different types of the pump. Piston pump may be the one that is most heavily used. Okay, now two categories like I mentioned, fixed volume pumps and variable volume pumps, and that's it. First we're going to take a look at the fixed volume pumps. This is very, very simple. No serious thinking needed because we're going to take this simple equation which is power is equal than the flow rate multiplied by pressure. That's same that in electronics, kind of the same that the electronics. And the flow rate multiplied by pressure. That's your power. Now, pump is operated by a motor which has a limited amount of power. And this will be the way to model the fixed volume pumps. So, and the way we can do it is that we simply take this equation and we take this mechanical efficiency into account, like how much energy, this mechanical energy can be converted to be hydraulic energy. And that's this mechanical efficiency number. And by taking that into account, that's going to be your equation to define how much flow rate can fixed volume pump produce. So you simply take this Q, you solve it from this equation, and you take this efficiency factor into account. That's your equation with one limitation. And one limitation is that there is a mechanical maximum due to the construction of the pump that it can produce. Now, taking this geometrical limitation into account, which is this maximum flow rate it can produce, that's your equation. So what do you do then? Is that you substitute the information about how much is the power, the maximum power that the motor running the pump can produce, and then the pressure, and that it is right after the pump. This is the one term, and then you compare it the mechanical maximum, and you're selecting the one that is introducing the smaller value. That's it. This, as mentioned earlier, is typically connected to pressure relief valve to make sure that the pressure is not increasing too much. That's a typical combination. Variable volume pump. And remember, let me say this to you one more time. So in the modeling of pump, the pump is assumed to produce flow rate. Flow rate. Flow rate. Why I say that? You got the idea, because what you're gonna see momentarily is, yes, in class quiz. So pump is producing what? Flow rate. Okay. So it's a flow rate that it is producing. Okay. Then variable volume pump. Now things becomes to be a bit more complicated. So we're going to use now, in this semi-empirical modeling approach, we can use again first order delay equation or differential equation to be more specific. And what I have in this first order differential equation is that I have here Q dot, which is not what I want, but I can solve the one that I want, which is Q. Now this Q is proportional between the pressure difference that you wanted to have and what you have. And if you have the pressure right after the pump, you don't need to produce any more flow rate. And that the flow rate that is currently produced is this, and this is how fast your pump can react to different situations. So the scenario is this. So you wanted to have the pressure, which is, let's say, 220 bars right after the pump. You want to make sure that that amount of pressure is always in your disposal, always in your use. Okay? Now, how is it you can make these 220 bars to happen? Is that you're producing the flow rate from the pump to this particular control spot here. Then you're measuring the control spot, and as soon as the pressure increases to this value, which is this reference value here, you produce normal flow rate. Simple like that. Because remember, again, this equation that I have wrote at each one of the slides today. You know, this is Q in, Q out. So as soon as this reaches the set value, you do not produce any more flow rate to this control volume. And you're adjusting the mechanical dimensions of your variable volume pump, and that will do the job for you. The parameters needed is this time constant and the K, that those you can get from manufacturer's catalog. Again, how? There's an example momentarily, and there's a detailed explanation in lecture material too. Okay. Load sensing pump. Have you heard about that? So you know how that works. Would you care to hear this one more time? Okay, so some of you know what's the deal with the load sensing pumps. Others, you have never heard. Or have you? Yes and no? No, you haven't heard about it. Okay, the load sensing is an extension of variable volume pump. You know, it too is a variable volume, so it can control itself to different scenarios, but more clever way than this constant pressure control, because the constant pressure, as the title says, make sure that right off the pump there is a constant pressure, nothing else. But this is still energy-wise may not be the most clever way to behave, because sometimes you need quite a bit of reserve in your system, sometimes you don't. And what you really wanted to do is that you want to sense how much extra or reserve energy is needed in your system. And you can measure that from actuators, which, you know, the typical actuator is a hydraulic cylinder. So you go and take the pilot drives, this kind of sensor signal right next to where the cylinder is operating. So cylinder piston side and cylinder piston rod side. Are you checking what are the pressures at the given time in those locations? And then you're adjusting your pump based on that information. You take the highest pressure into account, and then you make sure that this highest pressure plus predefined pressure difference will be in your use. Predefined pressure difference could be 50 bars or something. So when you need it, you have it, but you don't do it excessively. So you don't waste energy. That's the idea behind. Very much used in mobile hydraulics. How much you understood from that explanation? 0, right? Okay. So can I explain it using another kind of a drawing and try to explain it again? And then there's an outstanding YouTube video which we're going to take a look momentarily. Okay, here is my cylinder. This is what I mentioned as my cylinder here, hydraulic cylinder. So I'm measuring pressure here. So I'm taking the pilot line from that particular location, and I'm going to take it out to this subtle valve. This is the valve which is like this. So it is always selecting the highest pressure, nothing else. And I'm looking the pressure from other side of this cylinder here, and here based on this valve I'm selecting the highest. This information goes to my control signal, and you're using that to tune how much pressure is needed in this particular location. This pressure difference between this line and this line will be that predefined pressure difference, 50 bars or whatever you want. Let's take a look at the video, and then I will explain a bit more.
Welcome to Lunchbox Sessions, bite-sized industrial training.
Why this is not...
Hey, it's Carl here from lunchboxsessions.com.
It was okay.
This will be a brief introduction to load sensing pumps,
just a second.
sometimes referred to as flow compensating.
Where this line goes now? Speakers. Should go to speakers.
Welcome to Lunchbox Sessions, bite-sized industrial training.
Hey, it's Carl here from lunchboxsessions.com.
Big headache. Okay, this one. You see it now? What? You don't see it yet? You see it? You see it. Okay, let me just make this a bit bigger because I don't want to go back to the presentation mode anymore. Okay. Load sensing.
Welcome to Lunchbox Sessions, bite-sized industrial training.
Here.
Hey, it's Carl here from lunchboxsessions.com. This will be a brief introduction to load sensing pumps, sometimes referred to as flow
box sessions, bite-sized industrial training.
Hey, it's Carl here from lunchboxsessions.com. This will be a brief introduction to load sensing pumps, sometimes referred to as flow compensating. Our pump still has that very heavy spring, that major adjustment called the pressure compensator or the pressure cutoff for when we hit that really high top end pressure to make sure our system is protected. But it also has a weaker spring called the load sensing adjustment or the flow compensator. And that flow compensator is receiving information, feedback if you will, coming directly from the load, our cylinder, which right now is working at 300 psi. That's the pressure it takes to lift the cylinder and rod. And that 300 psi is being fed back to the controller and giving that spring a boost. I could tell that the spring is actually set to 300 psi. How did I figure that out? I figured that out because our pump outlet pressure is set at 600. So it's taking 300 from the load and adding it to the 300 spring setting, and those two pressures add together, those two forces add together to give us our regulated pump outlet pressure of 600 psi. This is different from a pressure compensated pump, which might be set at, say, 2000 psi at all times, and therefore using a lot more input energy. So in this particular case, we've got a pump that sets its outlet pressure just slightly higher than what's needed by the load. We've got to have some kind of a flow controlling device in there. This is our needle valve that's being used to set our desired cylinder stroke speed. But let's have a look at what happens when I add a brick to the brick stacker. Our load pressure has gone up to 600. But what happened to our pump outlet pressure? Somehow it automatically adjusted from 600 up to 900. What we're finding out is that we're always maintaining a 300 psi pressure differential, sometimes referred to as a 300 psi margin pressure when we're referring to load sense systems. Let's add one more brick, and this time watch the delta P gauge. The delta P gauge fluctuates for a brief fraction of a second, but quickly we find it returns to 300 psi, and we never really noticed any change in speed at the cylinder. The cylinder just kept moving nice and steady, and our pump found out that it needed to increase the outlet pressure setting automatically. So what we found out is we can have a pump that is set at a pressure that's just a little higher than what's needed at the load, instead of being always at the pressure cutoff pressure, which could be considerably higher. And because we know we want steady speeds to our hydraulic cylinder, we don't wish to see any fluctuation in speed. Every time we take a brick off the stack, or every time we add a brick to the stack, the pump knows to adjust itself accordingly so that the flow rate through the needle valve doesn't change. That's the nature of a load sense system. And that's a brief introduction to load sense pumps. Thanks for watching.
Clear, pretty clear. Okay, and I got the comment from online participant that I used incorrect terminology, because I think at some point I say fixed flow, so it's a fixed displacement, and that's what it is. So fixed displacement, because the displacement, the mechanical dimensions are unable to change. All right, thank you very much for that. And now comes the next challenge, and let's see how well it works. I think that I will go like this, because this is what we discussed already. So in a load sensing, you can have more than just one actuator you monitoring. And based that there is a one cylinder that is asking for the bigger margin, that's what this guy was calling margin pressure. You are controlling your pump based on that. So it's always the highest pressure that is used to control the load sensing pump. The key parameter can be obtained from the manufacturer's catalog, like it is shown here. So these are one of the important features that are offered by a manufacturer. But my first-in-class quiz is coming right next. So in hydraulic modeling, a pump is assumed to produce what? Pressure for a hydraulic circuit, oil flow for a hydraulic circuit, temperature for a hydraulic circuit, voltage to electrical circuit. And not yet, so it's not yet on, but let me, sorry, I haven't logged into the Socrative, so it's going to take me a couple seconds to do so. So you guys want to have a break, or you will take a break, no matter what. Okay, so let me launch. They have a different visual interface than usually. Okay, so here it is. So in a hydraulic modeling, a pump is assumed to produce what? Pressure, flow, temperature, voltage. Those are the options. And then what follows is that I'm going to spend a little bit of time to introduce One example related to hydraulic circuit modeling. And once I'm done with this example, then we're going to discuss about how to describe mechanical deformation in multi-body applications. Room name is not mentioned. The room is LUT, as usually. Oh, the secretive link. I don't know how you can get the link. I guess that you just typed the secretive to Google and it will take you to secretive. Okay. What else? Yeah, there was one more comment about this digital hydraulics that more component, more reliable. I mean that you have more problems. Yeah, could be, could be. Okay, so let me take a look. Oh, we got 44 answers so far, so I think I'm hoping we're gonna get more than that. If we're gonna all go up to the 60 something, that I think is roughly the number that will make me happy today. But we'll see. We'll see. Oh, with 50 answers already, so it's and the number is increasing. So what do you guys say? Can we go without the break today, or 5 minutes break? 5 minutes. So it's too heavy. It's too heavy. So what being the most heaviest today? Load sensing. What being the most complicated matters today that we discussed? Load sensing or pump modeling, cylinder, load sensing. Okay. All right. So let's do such the way that we will take a 5 minutes break. So 5 minutes. I'm gonna mute myself for next five minutes. You guys go and take some coffee and please come back in a timely manner. So, hey, online participants, we're still in a break, but we will be back momentarily. So, I was muted because of the break. Okay. Yes, sir. Okay, this is up to you guys, but I'm recommending that if the next week, Monday, is the last lecture, which is 29th of November, then the exam will be in a week of Monday, 5th of December. How that sounds to you? Yes, sir. In Lapland. Okay, do you have an internet connection in Lapland? You will. No, no. Okay, so I can be relaxed. So if you're in Lapland, I think that you should enjoy the Lapland. You said that you will be back on 7th. Okay, so my question to you is it enough if you do your exam from Thursday to Sunday, or you need more time to do so? Okay, so let me discuss with Surats. Maybe we can offer you 2 weeks' time to do the exam, a week and a half. Week and a half. So what you say? Are you not happy? How much? 2 weeks. That would be the best. 2 weeks' time. How many attempts? 10. No. I could give you 10 attempts if we can count the average. If counting the average, I will give you 10 attempts. You don't want that. Highest counted, that will be the easiest, of course. Okay, so let me put my screen back to you. So where is it? Here and this one. How is that? Okay, so we're gonna. So here's a little bit of sad news. So we only have here 57 students, but how is going to be the success rate? So game is on. 100? No, I would say 50. 50. 70. Well, it could be 72, but my guess is 50. So 50. So what are the others saying? So the numbers are coming, and the numbers are like 87, 98. That's a big number. That 99. 99. What about 100? So why not 100 then? It could be 100 too. Okay, so now they finally came to 100. So let me close in 5, 4. Yeah, I'm not gonna do this counting because last time I did the counting, you guys scored 100%, and that was a big, major disappointment to me. So it wasn't even a very close case. So oil flow is the one that it is producing, not the pressure, not the pressure. This is a modeling agreement we made. You cannot see. Sorry about that. Okay, so online participant they can tell you that the success rate was at 86. 86. Now let me check. Now it went in the wrong order again. So I need to do this and then this. Okay, and then one more thing, which is this. Duplicate. All right, so here comes the example that I mentioned. And now in this example, there's going to be another in-class quiz. So second in-class quiz will come momentarily. So I have here very simple hydraulic circuit. So it consists of a cylinder, this guy here, direction valve, and then the pressure source and the tank. And direction valve is connected via throttle valve, so there's a minor one component here to piston side of the cylinder, and then the piston rod side is connected to valve as well. So this is how it is. So let's create the equations needed to model this kind of the hydraulic circuit. First thing first. So the first and the most important step is that you need to make a decisions about how is that you discretizing your hydraulic circuit. Where are the places you need to compute the pressure? So it's all about where you can assume the pressure to be equally distributed. All right? Hose lines. We make an assumption that within the hose lines the pressure is equally distributed because we will not take the pressure waves into account. So meaning that there is a hose that is connected or connecting direction valve to throttle valve. In this hose line, there's one single pressure we're computing, and that's it. Then this throttle will introduce a pressure drop, and because of that, I need to make another computing right after it. But now I can assume that the pressure right after the throttle valve will be the same as the pressure next to the piston. My way back, I will take my connection, the volume in a piston rod side. This is connected to valve, and that's it. Just the one volume needed. One more very important decision you need to do. And this is decisions about the positive flow rate directions. You can do that anywhere you want. But highly recommended you do a drawing for it. And once you have a drawing, you can be consistent. If you think something in your mind can get disturbed. And because it can get disturbed, you can make so easily a sign mistake. But once you have put it in a writing or in a drawing, as shown here, then you do not make this mistake so easily. You need to do it because you need to know what direction you are assuming to be incoming and what direction you assume to be outgoing. Here, obviously, this is incoming, this is outgoing, with respect to this volume here. Whereas in this volume here, this is in turn incoming, and the direction here is outgoing. That's what defines what sign you need to use. One more time. So here, now there's a lot of drawings. Here, this flow rate is incoming because I'm making assumption that the positive direction is from right to left. This is outgoing because it's assumed to be the same direction than the previous flow rate. You can make it differently. That doesn't matter how you do it, but you need to be consistent because neighboring volumes, if you make mistakes, then the pressure will unrealistically start to increase and it never come back. It will go sky high or it will drop to the minus, and again, it will never come back. Okay, that was step number one, the most important. Rest is mechanical, simple. So you creating the equation to volume size. So the first volume is just a hose line, nothing else. Second is a hose line plus whatever the piston is traveling with respect to bottom of the cylinder. Third one, hose line, and then how you take the piston rod side volume into account. Very simple. Then effective bulk modulus for each of these volumes. So you need to compute a total of 3 different effective bulk moduluses. So that's how you can do it. So I'm not going to go into the details. It's another mechanical thing you can do. You can do it. Then pressures. Here is the second most important thing. So you're computing or you're creating the differential equation to compute the pressures for these 3 volumes, because you have 3 volumes in your system. Okay, the first one, we will get back to that soon. Second one, this is assumed to be incoming. So it needs to be positive in a sign as it is shown here. Motion upright direction is taking volume away from the control volume. So it needs to be minus in a sign. When the piston is moving this direction, that's a positive direction. When that happens, it compresses flow here. So it can be considered as a positive flow rate to my control number 3. Whereas the flow rate, which is shown here, is leaving. That must be negative. Okay. You got the concept. You got the plus and minuses, how it goes. You need to do something. You need to do this or you need to do that. You sure? Because your head is doing this, but your face and your eyes is doing that. So it's clear? So if it is based on it's all about these drawings. You take what arrow comes in and what leaves. So if I would next ask, what about the pressure P1, which is a P1 dot? Effective bulk modulus 1, volume size 1, and then how are the flow rates? Which is coming, which is leaving? Can you do it? You can do it. So you know what is a positive, what is negative. Incoming is positive, leaving is negative. All right. Pressures in a volume 1 can be computed as, and then the options are such that, you need to take a look at this. So it's assumed that the QA1 is coming in, QA2 is leaving. Then it's assumed that the QA1 is coming, QA2 is coming, QA1 is leaving, QA2 is coming, and both are leaving, which is correct. And just a second, let me put the Socrates on. So momentarily you will see, okay, where is my browser here? So let me take myself to next question. And we only have 2 in-class quizzes today. So now I need to go back here because otherwise you will not see it. And you don't see it at all. Okay, just a second. Not yet. Okay. Would you like to get my consultation or you're okay? Because that will be for you. If you wanted to go and discuss with me, we'll be happy to do so. And I will be willing to step off from the camera too. And willing to mute myself. So what is the correct one? Let me see. I got some comments from online participants. And the game is on. What is the success rate here? You guys need some more time, or are we okay to continue? Okay, now there is a question. There's cases about the success rate like 110%, 100%, 93%. I would say the 93 would be more close to reality rather than 100%, because 100%, that's not is not going to happen. It happened. I know that too well. Okay, so can I go? Okay, so I'm going to skip that because the right answer was visible, so I'm going to go back to that slide. Modeling the valves and the flow rates, so that's going to be my next task to do. So we have 1 direction valve and 1 throttle valve. Each of these valve components we have discussed earlier. So this one here you can compute when you know this pressure and this pressure. And you're using this simple semi-empirical equation to do it. And the valve position, you first describing the valve position, and once you know the valve position, you're using these semi-empirical models to describe how is a flow rate. And then finally, and the force produced by a cylinder. So once you know the P1, P2 and P3, that's it. That's all you need to know. And that's about the hydraulics. Next, which is, I think it is 20 minutes, I'm going to spend to explain you shortly introduction to flexible bodies. Why? Because a couple of years back, we all professors, we received a letter from student union. I think you all member of that union, and the union was unpleased, unhappy about the fact that professors are not explaining enough what exactly they do in their research. And they was hoping that students will get more involved with the research we do. And so you asked this. It wasn't me, so it was you. So now what we'll do to make student union to be more pleased. So I'm going to tell you a little bit about how is that we can model flexible bodies in multi-body framework. And we'll see how much you're going to like it. This will be the subject matter that we will revisit in a course entitled Simulation Laboratory Course, which, by the way, is the best course in this university. Guess who is a lecturer? Correct. So it's going to be me. And I enjoy that course big time because it's more laid back than this one. So it's not as tight scheduled than this one. This is unpleasant course in the sense that we're a little bit in a hurry all the time. So I'm unable to tell my stories about this and that, which you may not like it so much, but I like it big time. All right. So it's the best course in my mind. if I can clarify the situation a little bit. All right. So okay. And then they're saying flexible body, so that's dancing me. Yeah, it's not going to be dancing me because I'm not that flexible. But let me take back to myself to, you don't see it now, but soon you will. Duplicate. Is it coming? Yeah, there it is. Okay, I want to show you this success rate. Success rate of this particular question now is not, it's going kind of weird way. Okay. Where is this? Oh, there. Okay, 84. 84. It's good. It's really, really good. And let me take myself back to that. So this was this question that I was asking. What is coming in and what is leaving? So obviously, this one is a correct answer. Okay. Anyways, back to the flexible bodies. And as we're kind of running out of the time, I might not this. I might continue a little bit about the flexible bodies on next week, Monday. But the flexible bodies, if you take a look at the publications made by my team in LUT University, many of them, really many of them are related to how to describe mechanical deformation in multi-body applications. So the research is related to method called finite element method. So are you guys familiar with that? Okay, that's what we do. So that's good part of our daily dealing. We do also this real-time simulation, deformable ground modeling. We're combining artificial intelligence to simulation and many kind of other things. But main body of our publications are related to how to describe deformable bodies. And I will give you a short introduction to that subject matter. We are not going to step into equations, but if you want to somehow torture yourself, if you want to penalize yourself, this will be a great way to do so. So you just printed out the papers we have made and you read it, and it hurts physically because the kind of the way things are explained are not so easy to follow. Anyways, so I'm going to explain you three different methods, and each of them are having certain advantages and disadvantages. They can be used to describe deformable bodies. Now, when you're describing deformable bodies in multi-body framework, you end up to have a finite element procedure which is capable to describe nonlinearities. And that's a big challenge, because I'm sure you have used a finite element method, but linear finite element method. What we have developed are methods that are capable to capture large deformations, large rotations. Combination that is a big problem computationally. Anyway, so this is a long story, but today is just a highlight. So the methods we've been busy with are mainly this floating frame reference formulation, very complicated name, by the way, but it is kind of combining finite element method, conventional finite element method, with modern reduction technique and multi-body system dynamics. And then there is this lump mass approach, which is not so popular anymore. It used to be popular at the time that I was young, 5 years ago. So a bit more than that. You know, it was very popular at the time that I made my doctoral dissertation 25 years ago. So it's exactly 25 years this month. So it's quite a while ago, but it's not used anymore. And then the method we're doing awful lot of developments, and that's the absolute nodal coordinate formulation. Okay, I'm going to skip this explanation. So I think that I mentioned this to you. So everybody, every single component in real life is not rigid. There is no such thing like rigid bodies. But is mechanical deformation significant enough that it needs to be accounted in dynamic simulation? This is hard to answer. Sometimes it is so significant that you cannot assume to your model to be rigid, but you have to take the mechanical deformation into account. When you need to do it, that's like I say, very complicated questions. I could give you some rule of thumb, but generally speaking, that's a big challenge to know when it needs to be made flexible to get accurate results. But anyways, flexible, how the body deforms, can be defined to two different big categories: linear deformation and nonlinear deformation. And depending which one is your case, kind of like, to speaking in a more proper way, is small deformation and large deformation. And it's all about defined like how is a relation between the strain and displacement. Okay, what is displacement? Let's get started from that. Well, the displacement is like how far off you take your body from the original undeformed configuration. So if I have a cantilever beam, and if I deform the cantilever beam like this much, I will have here at the end of my beam displacement that is defined by u. Displacement is a function of the length of the body, because u is going to be different here in the middle that is at the end. So this is displacement. Now in finite element method, you're defining how is your relation between the displacement and strain that takes the place in material itself. And how is this relation? And you can, in most of the cases, you can assume this relation to be linear. Strain is this definition you have seen many times. And from strain, you can take one more step ahead, which is stresses. If this is a linear relation, which is very common when you have a small deformation, it comes with the consequences, which are easily visible when you look at the cantilever beam. Because in a cantilever beam, when you're loading the free end, it will deform as is shown in this picture. Looks natural. But there's one major assumption here. And the assumption is that deformation in axial direction is not accounted. And that becomes to be unnatural. If you're increasing the force, if you keep on pressing the cantilever beam, it will deform in a way, I'm going to make this drawing here. If it is originally here, this is where you're pressing it. It will deform like this. It will stay in this loading line. And that's not going to happen in a real life. That's not going to happen because in a real life, when you have a large deformation, it will deform like this. And there's going to be displacement in axial direction too. This is called geometrical nonlinearity because this deformation affects to the axial displacement as well. Okay, this is very common in real life. You can see that in many applications. What is not very common in real life is this material nonlinearity. This is this stress-strain relation. Stress-strain relation. You know that how the still material behaves. They behave in a way that, let me see if this is a clear. So if this is a strain, this is a stress. Most of the case, they behave linearly. Meaning that if you're loading this cantilever beam, this relation is linear. And when you take the force off, it comes exactly where you started from. Well, it comes back to the undeformed configuration. But if you really take a big force, I'm referring this again, something really big, what can happen in real life is that you can introduce permanent deformation. And that's, you can see when you take a look at this relation becomes to be nonlinear. So you're moving something which is called plastic zone. Now, the consequence of that is that when you take the force off, you're no longer coming back to the original configuration, but you're coming back here. When this is related to displacement, there is a permanent displacement. So it left to be deformed. It's going to be something that is not looking very good. Now, in machinery, in mechanical engineering, of course, this plastic deformation takes place every now and then. But if you think about the mobile applications, it's not common. And it's not common because it means that you have a crane, you lift something with your crane, and it's left deformed. It's left to be plastic already. That's not the good design. That looks awful. It can happen if you really make a major mistake. But usually, the designers are good enough so they don't make a mistake like that. So anyways, computationally, this relation, when this relation displacement strain relation is nonlinear, then you can capture this large deformation. Where you need it? Well, let me just give you a couple examples. I'm going to get back to this, but you need it in a certain very complicated components like belts, cables, wire ropes, helicopter plates. Those are the cases where you need to take this into account. And here's a development where LUT University is being heavily affecting. So remember multi-body dynamics, it started already 40 years ago. And it started from assuming that every single body was a rigid. And soon became clear that, okay, this kind of assumption is not good assumption because there are cases where mechanical deformation is significant enough that it affects the performance. And when you do the assumption with the rigid bodies, your simulation responses are incorrect. And to increase the accuracy of the models, there is a method to describe this deformation. This time, assuming that this U-strain relation was linear. You can do a lot with that. But then the final step, which is at the moment somewhat available, is that you can model even the belts, something where this relation is nonlinear. So LUT started from here on, making contribution about this, particularly to this. So now I hope that the student union is getting happy. But there's going to be much deeper story than that, because I would like to go with certain level of mathematics here. Okay, so I'm going to explain you one method, and then the rest I will leave for next week. So here's this method that take me back to my um, childhood, teenagers year, or when I was a doctoral student. Let's put it this way. So at the time, it was a method which was called lamp mass approach, very much a valid one, and it's a very simple concept because it was based on the fact that you take your original body, beam-like body typically, hard to be used in any other shape of the bodies. So cells and other geometries really, really hard to capture. And you model this beam-like body by using number of rigid bodies. So original body was replaced by number of bodies. And the number of bodies were connected together via spring elements. Spring elements that introduce the spring coefficients to each of the 6 directions or degrees of freedom. And it makes it behave as a deformable body, even though that it was a collection of rigid bodies. This was an okay method, but remember what I mentioned about numerically stiff problems. This is a good example what can easily lead you to numerical difficulties because of the numerical stiffness. If you think about this beam-like body and you think about the deformation associated to this kind of bending motion or bending deformation, is usually associated with a somewhat low frequency, 50 hertz or so. But if you think about the axial deformation, you have a beam-like body and you wanted to compress it, that frequency is very high. It can easily be, if this is a 50 hertz, this axial deformation can be 2000 hertz. And here is your problem. So you have high frequencies, low frequencies. And this is something that integrators usually are suffering big time because they can recognize this high frequency. They will see that there's something going on with the high frequency. So they are looking this high frequency very accurately. When they're looking this high frequency very accurately, they are adjusting their time step to make sure that they can recognize this high frequency. It doesn't make much of a difference in practice, but they tuning themselves to look at this minor thing. And that's what slows down the computation. It's like, you have this cantilever beam. You press it like this, so there's going to be axial deformation and bending. And when you look at the response will look like this, time-wise. This is time, and this is this displacement. But when you're magnifying this curve here, when you take a close look about this curve, you will see that there is a small vibration like this. And integrators immediately detect, hey, there's a high frequency. I want to take a close look about that. And that's what they do. But how much it makes a difference? Not much. Okay, so that's the first method. And then the second one, this is how it behaves. And there are a few examples. We're going to take a look at these examples. We can take a look at what is a good and what is a bad thing about it. And on Monday, we will continue about the floating frame reference formulas. And I will show you some exciting things related to that method, how we can model bones and stuff, and how is that we can use the absolute Noda-Kone formula. So with the super exotic things. But don't come. Please skip. Yes, so we may be going to take, because you're not coming, so you said that you're not coming, right? Okay, so maybe I'm going to do the lecture in my office, so this much on. Okay, that's one possibility. Okay, thank you very much. See you on Monday. Hold on, I'm going to